Hi again everyone, Chris Tisdale here again. In this presentation I'm going to continue my series of videos on complex numbers. Now in previous presentations we talked about complex polynomials and how to factor them and the factor theorem, and we did some examples. Now in this video I'm going to continue on this tip with another example. So let me share my screen with you and we can start. All right, so this is a reasonably long problem. We're given a polynomial, p of z, which is a degree 5 polynomial. You've got real coefficients. That's important. We are asked to do a few things. We're asked to show that p of 2i equals 0. So 2i is a root of p of z. We're asked to illustrate. Oh, hang on. Let me just. There we go. Okay. So we're asked to show that p of 2i equals 0. So 2i is a root of the polynomial. Secondly, we're asked to illustrate that z squared plus 4 is a factor of the polynomial without long division, and also find the other quadratic factor, and thus factorize p into linear factors. Okay, so let's just review the basic theory of complex polynomials. You've got a complex polynomial here of degree n. There are four main parts. First of all, the fundamental theorem of algebra. Every polynomial of degree n has at least one root over the set of complex numbers. Okay, that is, there is at least one number alpha such that p of alpha equals 0. If the coefficients of the polynomial are real, then solutions appear in conjugate pairs. If alpha is a root, then the z minus alpha is a factor of p of z, and p of z may be written as this product of linear factors where the alpha i's are the roots and the a sub n is this coefficient. So this is like a factor theorem, if you like. Okay, so the first thing we're going to do is show that 2i is a root of the polynomial. Now this is pretty easy, and I'm not going to do all the calculations for this, but the critical thing to remember is that the imaginary unit, I, satisfies I squared equals -1. So what you would do, you would put 2i in for z, okay, and you would expand this. Remember, I squared equals -1, and you will get 0. Okay, so what does this tell us? It tells us that by the factor theorem, z minus 2i is a factor of p of z. Now, because the polynomial has real coefficients, if we know one complex valued factor, the conjugate must also be a factor. So since the coefficients in p of z are all real, z minus the conjugate of 2i is also a factor. So what is the conjugate of 2i? The conjugate of 2i is -2i. So it'll be z minus -2i. All right, so we've got z minus 2i is a factor, and z plus 2i. is a factor. Now remember, in part B, we're trying to show that z squared plus 4 is a factor. If we take this and multiply it with this, it must also be a factor. So the product of this will actually give us this. So if you expand this, again, remembering that I squared equals -1, we see that this is also a factor. Okay? So we've done it without division, right? Now also find the other quadratic factor. Now it says you can't divide up here, but it says nothing about not dividing in the second bit of B. So that's what I am going to do. Okay, so let's divide z squared plus 4 into our polynomial. And we should get something like a cubic because this is degree 5 and this is degree 2. Actually, before I should put actually, let me take a just fix it up a little bit. Okay, so I forgot to write the 0z. Okay, so we've got this 0z to the power 4 plus 4z cubed minus 8z squared plus 0z minus 32. Okay, so let's just step by step divide this in. So that into that goes z to the power 3 Okay, so I've multiplied that by each of those terms, and you take this away from that. So you will get 0 there. Bring this down. That will divide into that -8 times. And then that times that, that times that, that times that. Write that down here. And you will get the following. Okay, this taken away from that will leave you with 0. Okay, so now the polynomial p of z can be written as the following. Okay, now you see here this is a cubic. We want to find the other quadratic factor, but this cubic is nice because it's the difference of 2 cubes. Okay, 8 can be written as 2 cubed. Okay, so I can actually get what I'm looking for just by looking at this difference of 2 cubes. Okay. Okay, so this is one quadratic factor, this is the other quadratic factor, and you've got this linear factor here. Okay, so the other quadratic factor is z squared plus 2z plus 4. Okay, the last thing we want to show, factorize p of z into complex linear factors. Well, we've got 3 of those linear factors. There's the roots, I beg your pardon, there's one. And from this and from part A, I know 2i and -2i. This can be expanded to z minus 2i, z plus 2i. All it is now finding, splitting this up. Okay? So, so how do you do it? Well, you can look at the roots of this quadratic polynomial. Okay? And you can apply the quadratic formula to that and actually write down the roots. Oops. Okay, you can obtain the following. It's going to be z squared plus 2z plus 4 equals z plus 1 minus I root 3 and z plus 1 plus I root 3. Okay, now I haven't put in all the steps for that, but it's pretty easy to apply the quadratic formula to that. Okay, so I can now finally write p in the factored form with linear factors. Okay, this will go to z minus 2i, z plus 2i. We've got a z minus 2 there, and I can write this as the following. And there you have it. Okay, there we have it. We've completed part C now. We were asked to factorize p of z into the linear factors. Okay, so that's my presentation. Hope you enjoyed it. Hope you found it useful. Thanks for watching this series on complex numbers. In forthcoming videos, I'm going to talk about matrices and linear systems. So I hope you can join me. Hope you can tune in for that new playlist on linear systems and matrices. Thanks again for all your support. I really enjoyed bringing these classes to you. If you have any suggestions, any comments, any feedback, you can always post a comment and let me know. Thanks for watching. See you later. Bye.